Hello viewer, welcome to our continuation of chemistry lessons, and we have been going on. This is our 80th lesson, and we wish that we continue even amid this corona pandemic. I want to remind you something that as we stay at home, as a student, don't forget to study, because life will resume maybe as normal in the future. That's our hope, that life will resume. So don't actually lose hope that maybe life is actually ended there. We are going to resume later than sooner. So welcome to our lessons. So we have been trying to actually engage you in chemistry lessons, and therefore don't forget to study, because the Kenya National Examination Council is actually preparing an exam which is actually going to test us in the syllabus that we are covering. So this is actually an advantage unto you, because we are now giving you an upper hand. Thank you. Welcome to our presentation this time, whereby in today's lesson, your presenter has always been Hilary Kikoske. We have been going together in our presentation. So today we are going to look at the continuation of electrochemistry, and in this electrochemistry we are going to look further on the electromotive the EMF of a cell, the electromotive force of a cell. So if you look at this abbreviation here, this is an abbreviation whereby we have EMF. EMF stands for electromotive force of a cell. So what is this electromotive force of a cell? Actually, we are going to see from our previous lesson, I think we learned that we have those cells, we have actually what we call the standard electrode potential for a given cell. Now, in this case, we are going to be now combining the two cells as we have been doing in the previous lessons on the electrochemical cell. So when we combine the two of them, what is the electromotive force? What is actually the voltage which is actually given by a given combination of cells? Now, in this, our objectives will be calculating the EMF of a cell using standard electrodes, standard electrode potential. We are using standard electrode potentials. So we are using the one which actually we have been provided, and therefore it will be our task just to identify those, and maybe as a question dictates, you are going to use that as it has actually been dictated. But don't forget the following, that in this calculation, the calculation of the inert value of a cell made of, for example, let's say zinc and copper. So zinc and copper has been actually the one which you have been using as an example, whereby you are saying zinc is likely to do what? To gain, to lose electrons than to gain, and therefore this lose electrons, this one is gaining electrons. So if you actually from this, the EMF of copper is actually we have positive 0.34. That is actually it's on or it's actually on the right hand side. Now then we have zinc, which has the E naught value of 0.77 volts. It's actually on left or lower and on the other side. So now we have zinc actually can be reversed to look like that on the other side, which actually we have now. The process here will be positive 0. So if you reverse this equation here, remember this equation here is the zinc ions plus 2 electrons. But in our case here, we have zinc losing electrons. And therefore, when we reverse this, also we are going to reverse here the electromotive force. Therefore, it's going to give us 0.77. So this actually reverse E naught value to derive a cell reaction or cell representation. Then, so the overall E naught value here will be E on the higher side minus E on the lower side. If you just take this the way they are, so you just say E on the higher side. Which one is higher here? If you compare positive 0.34 and negative 0.77, which one is higher? The one which is higher obviously will be what? will be 0.34, and therefore copper will be on the right on the higher, and zinc will be on the lower. So you say now E, or you say E not value on the right hand side. Now if you have, for example, a number line is like this. So if this is a 0, this is 0. Now if you place these values here, obviously we are going to place here 0.34, and then we are going to place somewhere here negative 0.77. Therefore, so it's on the what? Left hand side. This is left hand side. This is right hand side. So copper here will be on the right hand side. So that's why we are saying E on the right hand side. The one which is now what? Which is actually higher. So it is actually on right hand side in comparison to the number line. Because this is 0, negative 0.77, which is now same. Then this one is positive 0.34, which is now copper. So you say just use that example. If you have that, it is very simple. It's very simple to get actually the EMF of the cell, because just say if you know right and left, if you can place two values on the number line, then you can actually get this question without any problem. You can get this question without a problem. So it's a very simple question. Or now, if you understand now the one which is reduced and one which is oxidized, of course, if you look at this, copper here, copper is being reduced. Copper is being reduced from copper ion, which is positive 2, to 0. So it's actually E reduced minus E oxidized. Here zinc is oxidized from positive 2, 0 to positive 2. 0 to positive 2. That's why it's oxidized. So you can say E reduced minus E oxidized, if you understand that. But if you are not happy with this, you can actually use this one. You can actually use this one comfortably. But if you are not happy with that, you can use this one. E on the higher side minus E on the lower. E on the lower. E not value on the lower. So let's look at this. Now substituting this, we have now 0.34 minus negative 0.77. That means actually, you know, in mathematics you say if you have two same signs, it gives you a positive sign. Therefore we have here to be positive, and therefore you add the two of them to give you an electromotive force of 1.10 volts. Now that's actually an example, a perfect example. It's actually showing you how you can actually calculate. So overall redox equation, we have there copper ions plus zinc. It is going to give us zinc ions plus copper solid. So the overall conventional cell representation, we have here zinc, and then phase boundary, we have zinc ions, and then we have in 1 molar, and then we have what? We have here the cell bridge. Then we have copper ions, then phase boundary, then we have the copper solid. That is actually going to give us the EMF of 1.10 volts. Now let us look at this. Zinc and copper reaction has a positive overall E value. Therefore, it's actually possible, and thus zinc can displace copper from its solution. So we are saying now from our calculation here, the reaction is possible. Why? Because zinc here is actually on the other side, or is actually more reactive, and therefore, why are we saying that? Why are we saying this reaction is actually positive? Because now the E naught value here is positive, and therefore that reaction is possible. You know, there are some reactions which are not possible. Okay? But there are reactions which are possible. This is actually a possible reaction. This is a possible redox reaction. We have reactions which are actually not possible, which are impossible redox reaction. Why? Because maybe you have we have a solution of a more reactive metal and a metal of a less reactive metal. Therefore, it is not going to displace the other one. So, whichever way you actually do, it's not going to displace that. So, now let's look at another example here whereby we have magnesium and copper. So, from the table we know that copper is gaining 2 electrons. It gains 2 electrons, it becomes copper solid. So the EMF value, the E naught value here is what? Is 0.34 volts. Secondly, on the higher side or on the right hand side. Then we have magnesium here. Magnesium, you know, magnesium here is actually supposed to be losing the electrons, but in this case, it has been written like this. So that means here it is actually negative 2.337. The other one is on the lower side. So you have to reverse this to look like this. So we have magnesium ion, and then we have magnesium metal actually losing the electrons to become magnesium ions plus 2 electrons. And then you have also reverse this sign here. Then if you do this, you are directly. If you do using this method, you are directly. But if you are not happy with that, you can use this method here, whereby you say E on the higher, which is now positive 0.34 minus or E on the lower, which is now negative 2.37. So when you do that, or you say E on the right hand side minus E naught value on the left hand side. So you know I've told you that if you have a number line here, we have 0, we have positive side on the right hand side, then we have negative on the left hand side. So obviously negative 2.37 now will be actually the negative E naught value. So therefore it will be on the left hand side. And the other one, which is now copper, it will be on the right hand side. So if you know, say E on the right hand side minus E on the left hand side, you will get the same there. So substituting this, we are going to get now the E naught value here to be 2.71 volts. 2.71 volts as our E naught value for that. So the overall redox equation we have here, magnesium, copper ions plus magnesium ions, magnesium metal is going to give us magnesium ions plus copper solid. It's actually going to give us the E naught value of 2.71 volts. 2.71 volts. The overall conventional cell representation here will be we have magnesium phase boundary, then we have magnesium ions actually in 1 mole, then we have cell bridge, we have here copper ions, then we have phase boundary, we have copper solid. Then this is actually the E naught value of 2.714 volts. That marks actually the end of our presentation. But I want you, during your own free time, you have to attempt this question here, whereby we have here A, we have ions of A, plus 2 electrons, we're going to give us what? Maybe it's not actually clear here, but I think we are going to follow that. Give us A solid here. This one here is 2.90 volts, 2.90 volts. Remember, it's actually voltage. Then B, we have here P, which is amperes, plus 2 electrons, which is going to give us what? P solid, which is negative 2.38. Then we have here C. C here is actually half C2. Then it is going to give us what? C. I think we have here C ions here. We have C ions here. We have C ions there. C ions, which is going to be 0.00 volts. 0.00 volts. Then we also have here. We have here F, the same plus 1 electron. It's going to give us F ion, which is going to be 2.887. Now these are the questions that we are going to look. Now, which element is likely to be hydrogen? Likely to be hydrogen. I think you can answer that. What is the E naught value of the strongest reducing agent? Strongest reducing agent. Hope you still know the reducing agent. Strongest reducing agent. Now, number 3, calculate the EMF of the cell that will be formed when a half cells of B and D are combined. So B and D. So we have B and D. D here is actually D positive 2 plus 2 electrons. So going to give us D, which is actually 0.34, and then P is actually positive 2 plus 2 electrons. It's going to give us P, then negative 2.38. I hope you can construct that and give us ambition with that. So otherwise, that marks the end of our presentation today. Next in our next lesson, we're going to actually look more on our presentation. Thank you very much, and don't forget to subscribe at Mwalimu Sitonic to actually obtain more lessons on our presentation, because we are actually presenting lessons as usual in Form 4. We are going to carry out lessons which actually we know that we actually have them in our syllabus. Thank you.